In today's video, we are going to look at composite figures. Now, composite figure means that we're going to put a figure or solid or some sort of shape together out of multiple other shapes or solids that we know about. And so keep that in mind as we're looking through these problems. And we might need to consider how these parts fit together, as well as the pieces that we can figure out any areas or volumes of. Please do keep in mind that any of the formulas that I'm going to be using are all available on our formula sheet for our area and volume. And so if you need to, again, open that up, print that out, or have that open in a separate tab as you're working. But you will have all area and volume formulas available for you on the SOL, on our assessment activity for this unit, as well as your final exam. So let's jump into example 1. And so as I'm looking at this, it appears that we have a shape that's made out of a bunch of rectangles. And so don't forget, as we are looking at rectangular area, any area of a rectangle, if we go back to our formula sheet, again, the area is always going to be base times height of that figure. In other words, two of our sides that are perpendicular to each other. And so if we divide this up into rectangles that are smaller and a little easier to attack, we can just add the pieces together. And so the way I divided this, and again, doesn't have to be the way you do it, and you can definitely, pause the video, try the problem out on your own and see if you come to the same answer using different rectangles. But I used the small rectangle up at the top. And because it's basically 1 by 2 rectangle, I know the area on that one is 2. Then I used the small rectangle on the right, and actually I did both of those. Both of those are 2 by 4, so 2 times 4 gives me 8. And 8 on each one of them. And then I have 2 more rectangles on the left. I have the small little outcrop, again, 1 by 2 or 1 times 2 for our area. And then I just need to figure out the dimensions of that middle rectangle. And so let's label this one in red. And so if I know the entire length of the bottom segment of this figure is 9, but I also know that this section is a 4 and this section is a 1, well, if I take those away from 9, what's my leftover? Well, let's see, 9 minus 4 gives me a 5, minus 1 gives me a 4. So I know this section is a 4. And so then let's look at our height. Well, the left-hand piece here is also the same as putting the different sections together on the right-hand side, which we know from rectangles, the opposite sides will be congruent. And each one of those smaller pieces is 2, so I know the entire length is 6. And so the area of that larger triangle now is 4 times 6, otherwise known as 24. And so for our full area, all we need to do is add together all of our parts. So our full area is going to be 2 plus 2 plus our large rectangle 24, and then our 2 eighths from the right-hand side. And if we add those up, we get 44. And because we were not given units on this, but for area and volume, and you're going to see me doing this in all of our examples for these couple days, we do still want to mention our units. And because we were multiplying 2 items together, a length times a width, or our base times our height, 2 lengths multiplied means we're going to have units squared. And so that's our final answer. Okay, composite figures could also be thinking about leftover pieces. So in example 2, you'll notice we have one figure on the outside and we have some smaller circles on the inside. And our goal is to find the shaded area. And if we know that the outside piece is, or the outside shape is a square, we know that the bottom length 12 meters is the same as the right-hand side, also 12 meters. And so let's think of this. If we need to find the shaded area, what if we found the larger figure and then took away the empty pieces that we don't need to use? Well, each one of the empty pieces is a circle, and we know that the area formula for a circle is pi r squared. So that means we need to figure out what's the radius in each one of these. Well, if we have a whole bunch of circles and they all appear to be the same size, well, then let's just think about that length going across our circle. 12 meters Well, if I divide that up for our 1, 2, 3, 4 radii, well, 12 divided by 4 is 3. And so now I have enough information to find the area of the square and the area of each circle. So let's approach these one at a time. So looking at the area of our square, well, that's the same thing as a rectangle. So I know my area is going to be base times height, but I know my base and my height are exactly the same values. They're both 12. Technically, they're both 12 meters. I multiply that together and I get 144. Because they are both meters and we're looking for an area, our units would be meters squared. So now let's look at our circles. So the area of one circle, our formula is pi r squared, and we just figured out our radius was 3. So plug that in. So 3 times 3 is 9. So if I leave this in terms of pi, I have 9 pi. Again, it's area, so it's squared units, meters squared. And if we think of, well, we have 4 of those all put together to kind of take up that space in the square, we would take 4 times the area of our circles, or 4 times 9 pi meters squared, which is the same thing as 36 pi meters squared. Now, you might be wondering, why am I leaving pi in my answer? Well, pi is not a nice number. It is an irrational number. It is a decimal that does not terminate, does not repeat. And so any decimal I write down is going to be rounded off. Now, I know a lot of people like to use 3.14 as their pi. I like to keep it as exact as possible as I can. And so then if the problem is asking me for a decimal answer, well, at the very end of the problem, I can go ahead and plug this in Desmos or my graphing calculator and get the decimal answer at the end. And I will not have been using the rounded answer all throughout the problem to eventually get less and less accurate. So we are now ready for our final problem, which is, I'm going to put this in green, our total area is going to be whatever our square is minus our 4 circles. So our answer for our square was 144 meters squared. Our answer for our 4 circles was 36 pi meters squared. And again, ignoring those units, if you plug in your calculator 144 minus 36 pi, and again, don't forget, if you're typing this into the Desmos calculator, just type in the letters pi and it'll automatically convert it over to that symbol and that value. If you're using a TI calculator, then you can actually find the pi button right above your caret key. It's going to be over on the right-hand side that you'll want to look for that. When you plug that in, you are now going to get a decimal answer. So now we're not super accurate, but the more decimal places we use when we round off, the more accurate our answer will be. And so we're at approximately 30.90 meters squared. And so technically either of these would be a valid answer. All depends on how the problem is being, or the problem is being asked. Alrighty, example 3. So now we're looking at some new information. This one's asking find the lateral area and the surface area of the solid. So just as a reminder, or in case you haven't seen this before, there's 3 things that we can do with figures. We can find their surface area, which is the area of all the different surfaces, all the different faces all around the figure. We could have our volume, which is how much space it takes up. But this new thing, the lateral area, if we think of a figure, it's only asking about the sides, not the bases. So for example, if I was looking at my coffee cup, the lateral area is going to be, what's the area of the tall piece going around my shape, but it's going to ignore the top and it's going to ignore the bottom. So lateral area is just the side. And if you look at your formula sheet, again, feel free to pause the video and check that out real quick. Any of your solid figures, any of your problems like a prism or a cone or a cylinder, a lot of them have 3 formulas on there. So they have a formula for lateral area, again, all your sides. The formula for your surface area, which is everything, all your sides, all your bases, and your volume. And so again, don't have to memorize the formula, but you do need to know what the pieces are that feed into it. So if we look first at the lateral area formula for a prism, which is what we have here. So the lateral area formula is HP. Seems pretty simple. And so our H is actually going to be the height of the prism, which is the distance between the bases. So wait a second, I'm saying bases. When you look at a prism, there's actually two bases. It's kind of like a trapezoid where the parallel sides, top and bottom, we called those bases. Well, it's just like that in a prism. And so in this prism, we have a triangular prism, and I know that because I'm seeing these two triangles, one in the front, one in the back. These are actually our bases, even though they're not on the bottom. When you're looking for a figure, look for the side or sides that don't match the rest of them. So in a prism, it's going to be your triangular side or whatever your extra polygon is. All the rest of your sides, your lateral pieces, are all going to be on the outside, and they're all going to be rectangles. Alrighty, so H is actually going to be the 6 meters because it is the distance between the bases. So that's our height. Our P stands for perimeter. Technically, it's the perimeter of the bases. So P equals perimeter of bases. And again, that's noted on your formula sheet, so it's not something you have to memorize, but if you can remember that, that'll make your life a little easier and these problems go a little quicker. And so for that information, we need to know what are the sides along the entire base, and I'm missing one of them. However, any ideas? This is a right triangle. I know my two sides are 3 and 4. Well, that tells me I know my missing side is going to be 5. Now I could plug this into Pythagorean theorem, and we could do 3 squared plus 4 squared equals our extra side. Let's call them C squared. And if we work through that math, we would definitely find that C equals 5. But those numbers should also sound familiar because 3, 4, 5 triangle, that was one of our triples. So let's start plugging in. So lateral area, our height is 6. And our perimeter is adding all the sides on our bases. So that's going to be a 3 plus 4 plus 5. Oops, sorry. And so multiply or adding that out, that's really 6 times 12, which comes out to 72. And it's an area, so it needs to be meters squared. Alrighty, so that's our lateral area. Now let's look at our volume. Excuse me, not our volume, our surface area. So again, look up your formula first. And so I've already done that for you. That's HP plus 2 times a big B. Now H and P, we already found those. Those are lateral area. Now surface area, again, it's all the sides added up plus the bases. And so that's what this 2 big B is. It's the area, or big B is the area of a base. So that's area of the base. In other words, those red shaded triangles that I just put on the diagram earlier. So let's just plug in our info. So HP, we already know what that is. That came out to 72. We already calculated it. Plus 2 times the area of our bases. Well, our bases are triangles. And so if you look up your formula for the area of a triangle is base times height. No, it's a little b and a little h, and that's just referring to our red triangles. So if we fill that information in, and we're going to have 2 times 1/2 times our 3 times our 4, our base and our height of our triangle, the perpendicular pieces. If you multiply that out, you will get a 12. And 2 times 1/2 comes out to a 1. 3 times 4 is 12. Add those together, and we'll get 84. This is still an area, so it is still meters squared. And so there's our surface area. One way to check too, your lateral area should always be smaller than your surface area because it's only using sides, whereas your surface is using every single surface, including the bases, so it's including more area. All right, example 4. Surface area and volume of the solid. So again, I would always suggest with this, start by looking up your formulas. So our first formula, surface area, is pi r squared plus pi r, and we have an L. So in your formula sheet, L is labeled on the picture, and it stands for the slanted height. Anytime you have a pyramid like what we have here, although technically this is a cone, but it falls in the same family, the slant height is just this slanted piece on our shape. Now that's already labeled on our diagram, so we don't have to worry about that. So let's see, what about the R? Well, the R is the radius of the base. We know that. So 15 is our L, 9 is our R. We have enough to plug into this already. So let's do it. So pi times our 9 squared plus pi times our 9 times our 15. Simplifying each one of those out, well, 9 squared is 81. Again, I'm going to leave it in terms of pi just to make sure I have exact answers. See, 9 times 15, well, that gives me 135, still times pi. If I put those together, 81 plus 135 gives me 216 pi. And we are in surface area, so that means our units are squared, so centimeters squared. And then if I needed this as decimal, now would be a good time to plug that in your calculator. And that should come out to 678.58 centimeters squared. So either of these would be a valid solution, just depends on how the problem asks for it. That's our surface area. Okay, next part, it was asking us for our volume. So again, look up your formula. Volume equals 1/3 pi r squared h. And so looking at our variables, r for our radius, we already have that. H for our height, we don't know that info yet. It is not labeled on our diagram. But what kind of shape do you see in our diagram again? It's another right triangle. And so I could go ahead and use Pythagorean theorem. So 9 squared, see, I am going to label that as h. 9 squared plus our h squared equals 15 squared. So simplify that out. 9 squared is 81, 15 squared is 225. Subtract our 81 from both sides, we get a 144, and that's probably starting to look familiar. Our h is 12. This is actually a version of a third or of a 3, 4, 5 triangle. All the values are just labeled or multiplied times 3. And so now again, we have all the information we need to plug in. So 1/3 times pi times our radius, which is 9 squared, times our height, which we now know is 12. Of course, wouldn't be a bad thing to label that on the diagram. Multiply it out. So 1/3 times 9 squared times 12 all comes out to 324 pi. Again, I didn't do that in my head. I had it plugged into the calculator. And again, we could leave this in terms of pi. Now think about what we multiplied together for volume, which is a variation on length times width times height. It's 3 dimensions, 3 measures being multiplied. So our units are cubed. And again, if we wanted a decimal answer for this, we can just plug it straight in. So that's 1017.88 centimeters cubed. And again, notice I'm leaving a couple decimal places, but you always want to be careful, reread the problem and see if it specifies how you need to leave your answer. Alrighty, so we have looked at surface area and volume, and now let's put these together. So example 5 and example 6 and example 7, we are looking at more composite solids. So we're putting 3-dimensional figures together. And then to find our surface area or to find our volume, we'll just have to add the pieces together and think about the parts that we're putting together. So our first one, example 5, we're going to find the volume of the composite solid. Now we've got 2 figures in here. We have the pyramid up on the top, and we have a cube on the bottom. And it even said that in the directions, assume the bottom solid is a cube. So a cube, I know all of my sides, all my edges are all going to be equal. And so with the ones that are labeled as 8, I know all the rest of them will be 8 as well, including the sides on the base of that pyramid. Alrighty, let's look up our formulas and see what information we might need. So surface area of our pyramid, and I like to write it like this. I'm just keeping track of which figure I'm working with. You need to pick whatever notation or however you can organize your work so you know what's what on yours. So surface area of a pyramid, excuse me, we're not doing surface area, we're doing volume. So volume of our pyramid, our formula is 1/3 big BH. So again, big B is the area of the base. In our pyramid, that's this square that's on the bottom of our figure. And so don't forget, area of that square is going to be base times height, or length times width. And if all of the edges are 8, that's just going to be an 8 times 8. But we have a problem on this one. I'm stuck because the next thing we need to plug in is the height of the pyramid, and we don't actually have that. They gave us that 5, but 5 is not the height. That's the slant height. So the overall height is going to go straight from the top of the pyramid down to the very middle. And if I connect that with this piece over here, wait a second, I'm making yet another right triangle. And let's think about our measures. I know that slanted piece, the hypotenuse, is our 5. I know that halfway across that square is going to be a 4. Do those numbers sound familiar? I can think of this the same way. I don't know what our height is on there, so h squared plus 4 squared equals 5 squared. What number do you think goes in the h spot? Yeah, if we use our Pythagorean triple again, our h is going to be 3. Of course, you could always work the Pythagorean theorem out and it'll still give you the same answer. So that height I know has to be 3, and that's what I can plug into my work. Alrighty, so let's finish our calculations. So we have, wait a second, 1/3 times 3. Those actually simplify out to 1. And then I can even do the math in my head on this one. 8 times 8 is going to give me 64. It's a volume, so I know my units are going to be cubed. This is not inches, so I'm just going to say U cubed. Okay, we do need the volume of the cube next. So volume of the cube. Formula is length times width times height. Again, just what we saw on the diagram on the formula sheet. And all of the edges are the same, so everything is an 8. Well, 8 times 8 times 8 gives us 512, again, units cubed. And then our total volume, putting everything together. Our volume total. Just add up our pieces, so 64 plus 512 will give us 576 units cubed. So now let's look at example 6. So our composite figure has a cylinder and a cone. So here's the thing for this one though. They have some overlapping spaces. And if we're considering surface area, again, we only want the outside surfaces. So we're actually going to piece together pieces of our formulas that we have for each one of these figures and see if there's anything that we need to modify to make sure that we have just the information that we're looking for. So first thing I'm going to consider is, well, I have this cylinder and I have this cone and they overlap in the middle. So they overlap at this circle. So eventually we're going to want to take that circle out of the mix. So let's think about our cylinder. We could take our surface area of our cylinder, then subtract out that green circle, subtract out our overlap, but then we still have our cone. Now, again, we don't need an entire surface area of the cone. We just need that kind of almost triangular wrapped around piece. And if it's ignoring the base, is that surface area anymore? Well, that's actually lateral area of the cone. Again, we have that formula, so let's use it to our advantage. So let's figure out what measurements we need, and if we need to do any extra calculations, we'll do those. So surface area of the cylinder. Again, our formula for that, just looking that up on our formula sheet, that's pi r squared, or 2 pi r squared plus 2 pi r h. Okay, our overlap is a circle, and our area for a circle is pi r squared. And then our lateral area of a cone is pi r L. So let's make sure we have all of our variables. R is our radius, and because everything matches up in our shape so nicely, our radius on this whole figure is going to always be the same, which is half of our diameter 6, aka 3. So we know that, that's our radius. Our height that we need for our cylinder in the blue, well, wait a second. The height is always the distance between the bases, and this thing is kind of drawn on its side, just so it's easier to see in the picture. So this 50 is actually the height of our cylinder. That's what we'll need for our blue. Okay, our overlap, pi r squared. Well, the radius of that circle is still going to be the same as the radius of the base. So that's still going to be a 3. And then pi r L, again, L is that slant height, which is already labeled in our diagram. We don't need to do any extra calculations. We just need to plug in the things that we know from the diagram. So first piece, surface area, we're going to do 2 pi times 3 squared plus 2 times pi times 3 times 50. We're going to subtract out pi times 3 squared. And then we're adding our lateral area, pi times our 3 times our slant height, 5. Alrighty. So again, I'm going to leave everything in terms of pi. So I'm just simplifying the rest of the constants that are in each term. 2 times 3 squared, aka 2 times 9, gives me an 18 pi. 2 times 3 times 50 gives me 300 pi. And our green, again, we're subtracting out that overlapped circle, 9 pi. But we're still adding in pi times 3 times 5, in other words, 15 pi. Alrighty, so really we want to take 18 plus 300 minus 9 plus 15, and that all comes out to 324 pi. And we could definitely leave it in terms of pi if that's what the directions would have said. No units given, so I'm just going to say units squared because it's area. But if I plug that into the calculator, I'll get approximately 1017.88 units squared. Alrighty. So one more problem, surface area and volume on this one. So again, if you want to, pause the video, see if you match up then when you restart and, compare the work. Here we go. Number 7, surface area and volume. Let's attack surface area first. Again, let's figure out our formulas. So for surface area, we have 2 pieces. We have the surface area of the cone, and then we have the surface area of that dome, in other words, a hemisphere. So 1/2 of the surface area of a sphere. So let's think about this. Well, wait a second. Do we have any overlap on this one like we did on the other one? Yeah, we have that overlap with this guy, this circle in between. So really what I could do is, instead of finding surface area of the cone, again, we just want that tilted side piece. So actually, let's just do lateral area of the cone, save ourselves some time. And then 1/2 of the surface area of a sphere. Well, if a sphere is a full ball, 1/2 of that is just going to be the top of that dome. And so I don't need to worry about any overlap from the hemisphere piece of this. So again, let's plug our info in as we know it. So let's see, lateral area of the cone. Again, same formula as what we had before. That's going to be pi r L plus 1/2 the surface area of a sphere. Well, that formula is 4 times pi times r squared. Wait a second, I don't have all the info I need. The slant height is this piece, but the 12 that's being labeled is straight up and down. Technically, that's this piece here. What kind of shape do we need to use? It's another Pythagorean theorem problem. So let's call this L for slant height. We would want to do 5 squared plus 12 squared equals L squared. Does that pattern look familiar? Indeed, it is yet another Pythagorean triple. You could go through the Pythagorean theorem, but you will find that L is equal to 13 on this one. And so now we have all of our info because the only other thing we needed was the radius, and we have that already marked. So this is going to be pi times our radius 5 times our slant height 13. Again, not a bad thing to label it. Plus, well, 1/2 times 4, that's just going to be 2. 2 times pi times our radius, which is 5 squared. Alrighty, multiply those out. We're going to get, actually, let me move this over a little bit. So we will get a 65, 5 times 13 pi, plus 2 times 5 squared, otherwise known as 50. So putting those together, we get a 115 pi. We do have units on this one, centimeters, and its area, so centimeters squared. Or we could plug in the calculator and get 361.28 centimeters squared. Our last piece, volume, is actually the easier one. We don't have to worry so much about any overlaps. We just need to know what's all the space that these two figures take up. So for our volume, again, we need volume of a cone plus half the volume of a sphere. So let's plug that info in. So volume of a cone is 1/3 pi r squared h. We already solved out for that height, or we didn't solve out for it, it's marked as 12. And then 1/2 volume of a sphere is 4/3 pi r cubed. Plug in our info and we're good to go. So we have 1/3 pi times our r squared, in other words, 5 squared, times our h, which is 12, plus 1/2 times 4/3 times pi times our radius cubed. All right, again, don't worry about the fractions. Again, if you're using Desmos calculator, type them in exactly the way they look. So type in all of your constants around the pi. Our first one will simplify out to 100 pi. Our second will simplify out to 83.3 repeating, again with the pi at the end. And so we add those together and we get 183.3 repeating pi. We have units for volume, centimeters cubed. And if we change that over to a decimal, again, plugging in 183.3 repeating or 183.3333333, type in a whole bunch of threes and it'll keep it more accurate. That gets us to 573.96 centimeters cubed. Again, use your reference sheet to your advantage, but always have that by your side so you can look up whatever information you need. Let us know if you have any questions, and if not, go ahead and start in on your practice.